Chapter 7, Concurrent and Parallel Forces. Equilibrium is a state of a body in which there is no change in its motion. An object in equilibrium is not accelerating. Either it is at rest or it is moving at a constant velocity. We say that an object in an equilibrium has no net force acting on it. Many forces can act on an object simultaneously, but when the forces are added as vectors, the sum yields the zero vector. The study of objects in equilibrium is called statics. Equilibrium means that there is no rotation, there is no acceleration, and there is no net force acting on the object. In the case of forces acting in one dimension, the force on the left is pushing to the right. We say the direction is toward the positive. The force on the right is pushing to the left. The direction of the force is towards the negative. Summing the two forces leads to zero. The net force is zero. A cable supports a large crate of weight 1,250 newtons. What is the upward force on the crate if it is in equilibrium? We first draw a picture and label the forces. The weight pulls down and we label this force as F sub weight. The cable pulls up and we label this force F sub support. We sum the forces, F support minus F weight, and since the crate is in equilibrium, the sum must equal zero. We solve the equation for F support and find the support force is equal to the weight and must be 1,250 newtons. Four persons are having a tug of war with a rope. Harry and Maria are on the left, and Bill and Jill are on the right. Maria pulls with 105 pounds. Harry pulls with 225 pounds, and Jill with 165 pounds. With what force must Bill pull to produce the equilibrium? The forces on the left are pulling to the left and must be negative. The forces on the right are pulling to the right and must be positive. The system is in equilibrium, so must equal zero. From this we see the forces on the left must equal the forces on the right. The forces on the left are from Harry and Maria. The forces on the right are due to Bill and Jill. Inserting the forces we know allows us to find the force that Bill is pulling with, 195 pounds. Tension is a stretching force produced by forces pulling outwards on the ends of an object. Compression is a force produced by forces pushing inward on the ends of an object. The two figures show an example of tension. The figure on the left shows two identical tensions pulling on a weight. The figure on the right shows an object in equilibrium, but the two tensions are not the same. The length of the two ropes are not the same. In terms of vector components, the angles of the two ropes with respect to the horizontal are not equal. Even though the two ropes are not the same length, the system can still be in equilibrium. The crane in the figure is supporting a beam that weighs 6,000 newtons. Find the tension in the horizontal supporting cable and the compression in the boom. The horizontal cable is attached to the boom at point A. The separate vertical cable holding the beam is attached through the pulley at point A. We create a diagram and label all of the forces acting at point A. The forces are the tension in the cable pulling it to the left, T, the weight pulling down, W, the force of compression on the boom, R, and there is one more force acting at point A, the equilibrium force. The equilibrium force is the normal force. It is the boom pushing back on the cable. We need to be very careful here, for compression is not a new force. It is a net force that opposes the normal force. Therefore, in this problem, the compression is the sum of the tension and the weight. As before, we create a table with all the forces, known and unknown. Notice the compression force is not listed in the table. The net force is the sum of all the forces acting at point A. Since the system is in equilibrium, the forces must sum to 0. Summing all the x components yields the first equation. Summing all the y components yields the second equation. Looking at the y component yields the normal force, E, as 17,500 newtons. Since we now know the equilibrium force, E, we can use the x component equation to find the tension in the cable as 16,400 newtons. This allows the compression to be calculated. The compression is the vector sum of the tension and the weight. We know the tension and weight and their directions. These are right angles to each other. To find the magnitude of the compression, we use the Pythagorean theorem and get 17,500 newtons. We note that the compression force is in the opposite direction of the equilibrium force. A homeowner pushes a 40-pound lawnmower at constant velocity. The frictional force on the mower is 20 pounds. What force must the person exert on the handle, which makes an angle of 30 degrees with respect to the ground? Also, find the normal force. We create a diagram drawing and labeling all the forces acting on the lawnmower. We consider the lawnmower as a simple point. The forces are the weight pulling down, friction points opposite the direction of motion, motion to the right, so friction points to the left. The normal force is the force perpendicular to the ground and points up. The compression is the pushing force of the man, and in this case, the compression force is the same as the pushing force. As before, we create a table with all the forces, known and unknown. Notice the compression force is listed in the table as the pushing force, R. The net force is the sum of all the forces acting at the lawnmower. Since the system is in equilibrium, the forces must sum to 0. Summing all the x components yields the first equation. Summing all the y components yields the second equation. The x component gives us the compression force of 23.1 pounds. The y component gives the normal force at 51.5 pounds.